Please join me in welcoming Pete Wurman, Chief Technology Officer and Technical Co-Founder at Kiva Systems. Pete is the Chief Technology Officer and Co-Founder at Kiva Systems, where he oversees hardware and software research. Prior to joining Kiva, Pete was an Associate Professor of Computer Science at North Carolina State University, where he did research on multi-agent resource planning, game theory, and computational mechanism design. Pete holds a BS in Mechanical Engineering from the Massachusetts Institute of Technology and a Ph.D. in Computer Science from the University of Michigan. Please join me in welcoming Pete Wurman. Thank you.
Thank you. So this is a little unusual, and I was on a panel already, and I told you some stuff about Kiva, but I'm going to go ahead and give the talk. I'm going to give you a lot more detail now about Kiva. Some of the background stuff might overlap with some of my comments from earlier. And hopefully there'll be some time maybe for questions. I don't know if we're not really set up for questions, but we can try to do that at the end. We've been talking a little bit about Kiva, but first I want to make sure everyone really knows what it is and what it is that we built and deliver. This is a video from one of our distribution centers, and it's actually one of the facilities, the first ones we brought online. This particular warehouse runs at a Staples fulfillment center, and it grew over time into this system that you see in the video. Basically, what we've done is put all of the inventory that the warehouse carries on shelves, these little blue shelves, and then carry those shelves around with the little orange robots. We deliver them to stations on the periphery where the workers' job is to pick things out of the boxes on the shelves and put them into the boxes that are being shipped to your house. So this is that hard task I talked about earlier about finding the right thing and being able to get it out of a box and put it somewhere. Her job is very directed, so she's given a laser points at the bin where she's supposed to pick the product from, which we'll see in a second. It's shining right there. And she picks one or multiple items from that bin. She scans them to confirm she got the right item. A light flashes right over her the box she's supposed to put it into. She presses the button to confirm she did that. When the order is complete, she pushes it onto a conveyor and it is carried over to the shipping dock. And as I said earlier, it turned out that in most traditional warehouses, people spent about 2/3 of their time walking. By eliminating that part of the task and letting the humans focus on the hard part, the picking and packing part, we're able to make them 2 to 4 times more productive. Some of our customers have actually seen like a 9x increase in productivity. Over the years, we were able to sell systems to a large number of customers. This is the list. And you see on here a lot of pretty well-known top-tier retailers like Walgreens, Staples, drugstore.com. If you have kids, you might know of diapers.com, now called Quidsy, The Gap, Saks Fifth Avenue, and then a few others that are more business-to-business kinds of operations, like DJO sells medical equipment like knee braces to doctors' offices. OMI is in a similar business. Walgreens is interesting because that's actually what's called a retail restocking application. The things that they pick in the Kiva warehouse are then sent actually to the stores, and then those items are put on the shelves. So any Walgreens you go into, when you look at the cosmetic aisle, all that stuff comes from a warehouse run by Kiva Systems. We also have 2 facilities over in Europe for 2 of our customers. And so we're building all of the robots and all of the other stuff in Boston, shipping it internationally now. As we grew our business, we kept our eyes on the top 100 retailers because that was really, especially the internet retailers, those were really our prime targets. Those were the people who had the hardest and biggest pick, pack, and ship operations and the ones who could benefit from our technology the most. And we were doing a very good job of penetrating that market. And all the orange boxes are Kiva customers. And some of them are not really candidates for Kiva customers. They sell other kinds of things like Netflix, which streams video for the most part. But whenever I would be on an airplane or somewhere and describing what Kiva was and what it did, everyone would always say, oh, you mean like an Amazon warehouse. They never said like a Walgreens warehouse or a Staples warehouse. They all said, oh, like an Amazon warehouse. So we always had to say yes, but they don't They don't have any Kiva systems, although over the years they actually bought 2 companies that ran Kiva systems. And we used to tell our prospective customers, if you're looking to be bought by Amazon, you should install a Kiva system, because that seems to be the trigger for getting acquired. But eventually, Amazon really did come knocking, and as we mentioned earlier, they bought Kiva 2 years ago. So not just our customers now, but we actually are owned by Amazon. So what is the business problem that we set out to solve? Well, it's really focused on a slice of the logistics market, particularly on the distribution network inside the 4 walls of the warehouse. And there's several different subsets of that. I mentioned some of these are direct-to-home e-commerce things. There's also business-to-business, like most of Staples' operation is really business-to-business, sending office supplies to your offices. And then there's the restocking examples like Walgreens. And then within the building, there's 3 major types of activities going on. You have to receive all this inventory and store it. Then you have to pick it and put it into boxes. And then you have to ship it and sort it all and get it to the right dock. Traditionally, this was a really hard problem. And this is an old image from a few years ago of a typical Amazon manual warehouse. And you can see just here acres of boxes and pallets on the floor. And it's hard to see, but there's a few people walking around out there with carts. There's someone over here. It's hard for me to see him at this angle. And so these people used to walk 8 to 10, 12 miles a day in the process of doing their job. Well, what is this facility really trying to do? Well, they do 3 things. They take incoming pallets and they ship out outgoing boxes. And in the process, they store them for the products for a little while. They might move them around within the warehouse. But what the real value added of the operation is getting these 3 teddy bears out of the cases they came into and sorting them by getting 1 of each and putting them into a box that's going to be shipped to your warehouse. So it's really the sort task that where the facility's adding value. And while they're trying to do that, as in every business, they're under constant pressure to do it faster, do it more efficiently, with less labor, and more accurately. So it turned out my college roommate from MIT days had gone off and he had got his MBA at Harvard, as I mentioned earlier, and he was working at a company called Webvan in the early 90s, late 90s. And Webvan, it turns out, is probably the poster child for dot-com busts. They raised $500 million, and then they had an IPO, so their total capital spent was close to $1 billion. And they were doing grocery home delivery in the San Francisco area. And what they had a very compelling business model when they started. They expected people to buy $100 worth of groceries. In groceries, there's not a lot of margin on, so it was going to cost them $70 to put the groceries in the warehouse, which gave them $30 of gross operating margins. And then the business plan called for picking that stuff and putting it in the totes that they were sending to your house for $10, and then getting it from the warehouse to your house for another $10, which meant they could make $10 on every delivery. Unfortunately, the early reality was not nearly that good. Actually, people were buying more groceries. That was a good thing. So they were spending $120 per order, and that was costing $80 to procure. So they had $40 of gross operating margin, but it was costing $30 in the warehouse and another $20 to deliver it to your house, because they just didn't have the density of deliveries to keep the costs under control there. And it cost another $10 because they weren't doing it very well, and so the ice cream was melted or the wrong kinds of pears were shipped to your house, and so they were handling a lot of phone calls, which cost them another $10 per order. So they were actually losing $20 an order. They thought they'd make it up in volume, but they didn't really have a chance to do that. The warehouse was a combination of a typical manual process and the latest and greatest technology available at the time, which was these kinds of carousel systems which they had installed. So they have miles of conveyor, and the conveyors route the totes. These totes are the customer orders. They route them to all of these stations where this operator is going to pick things out of this carousel. It's like think of a giant clothes dry cleaner's rack. It just can go spin product around and around and then stop when it has the product you need and stops in front of the operator. So she's got 3 of these things trying to keep her busy. And even in this video, you can see she spends a lot of time waiting for the devices to spin. It stops, the light goes on, she can step on the mat, pull the product out, and put it in the tote, and then wait a little bit longer. Still, this was way better, where the other operators were getting about 40 lines per hour, items into a tote per hour. She's getting about 200, so it's a big, for a lot of capital, it's a big productivity improvement. But it also was a very fragile point in the distribution network, or the facility, because if you slotted the wrong things into this device, like you put the weekly newsletter in there and every tote needed that newsletter, everything had to come to this station and the conveyor backed up and ice cream started melting and everything just went wrong and people were running around trying to fix it. So this was Mick's experience. He came into Webvan towards the end. He spent a year there in the building trying to help the operations figure out how to improve the warehouse, but eventually they pretty quickly ran out of money and went out of business. But we know, even back then, the growth of e-commerce was projected to increase at a good, steady 10% year-over-year growth rate, and it has held that steady for the last 10 years. So he knew that this was going to be a big problem. And really the problem was that traditional warehouses were kind of designed for moving cases around. They weren't very good at this picking individual items out of cases and sorting them in small quantities into outgoing boxes. So Webvan folded and Mick was in California and he spent a year thinking about this design, this problem, and applied some pretty typical brainstorming things like what happens if you do this at the extremes? What if labor was really expensive? What if labor was really cheap? And through those brainstorming exercises, he came to the idea that, well, if labor was really cheap, what I'd do is just hire 10,000 people, each of which were holding one item, stand around in the warehouse, because labor's free, basically, and when I need something, I'll call for it, and that person will bring it over to me. And so we were really, as I said, we were roommates in college, and he was in California, I was in North Carolina. But I'd have reason to go to California, and he'd make up reasons to come visit me. We'd spend weekends working on this problem. And he said, I have this idea. I think you could do it with robotics. Do you know how you could do it? How could we build this? And so that's how he got me involved. And since we've talked a little bit about Legos, we actually built really small, little tiny prototypes out of Legos. No robotics kit at all, just like really tiny things with wheels. But we were really driven by this vision that, forget the robotics, it happens that robotics is the solution, but the business problem is very simple. To fill an order, you'd like to have an operator who can just stick their hand out, the product's there, they grab it, they put it in the tote. The totes and the outgoing orders just show up, so there's no work going into that effort, and you can just fill these orders as efficiently as possible and let the humans do the task that they're particularly good at in this scenario. So with this vision, and this vision is what really drove us through the whole program, we got some seed funding and started hiring people. So this is an old picture of the first 6 people. It shows also the original prototype robots. One of the other key people is the other technical co-founder here, Raf DeAndrea, who was very well known for having won 4 of the first 5 small RoboCup competitions. So he and his team from Cornell were just really innovative, and they did a really super job in those early competitions, and so they were very successful. And he was actually just going on sabbatical at MIT when Mick decided he was going to move the company to Boston, and I was going to participate, but I was more of a software guy, so we needed someone with a robotics background. And through a friend, we got a hold of Raf. A week into Raf's sabbatical, he met with Mick, and then he canceled his sabbatical and helped start the company. So the innovation is really simple. To make it all work, we just need 4 basic things. You have the inventory pods, which hold the inventory. The drive units, we call them the robots, that can lift the shelves about an inch off the ground and drive them around. And then the stations where the humans do the work. And in addition to all of that, there's a server rack in the closet where all the servers are that run the system. That's where most of the stuff that I've worked on exists and works. There's a lot of really powerful benefits to this concept, but one of the key ones is that now the whole warehouse becomes this massively parallel process. Instead of having very serial process, like I have to walk from location to location to pick things, or I have a conveyor that moves every outgoing box past every picker. Every picker here is working at their own set of orders at their own pace. So this is actually one of the very first simulations we did. It's a top-down view of a potential warehouse. And over here on the right side are stations with little queues the robots drive into. They deliver the pods to this little green pick worker who's doing work, and then they release the pod back to storage. But what's also really cool about the fact that we've made it all parallel is we can apply some really nice algorithms to the process. And so this is a video, actually the exact same clip, but now we've colored all the pods by their velocity, which is a measure of how popular the products are. So the red ones are very popular products, and the blue purplish ones are very slow products. And by applying some optimization algorithms, the system knows to store the popular products near the front and the slow-moving stuff near the back, which means most of the drive robotic activity is near the front, which means they have shorter trips, which means you can do all the work with fewer robots. And the whole thing scales to ginormous scales. This is not a real warehouse. It's another early simulation showing that you could do this with 100 stations wrapped around the outside. It's been a really interesting and fun project to work on for me personally, and I think it's been a great example of how robotics technologies are becoming more and more broadly applicable. What enabled the robotics was kind of this, at the time we were starting, which was 10 years ago now, we were just starting to see really effective, inexpensive sensors. Computational platforms were becoming cheaper. Wireless was really hitting its stride so that we could dream of putting thousands of robots in a building all sharing the wireless network. And then we took some very practical and careful approaches to taking advantage of these innovations to produce a reliable system. For example, before I go into the next slide, you can't see it in this picture, but the navigation system is little stickers on the ground. It's not fancy indoor GPS or anything else. Underneath this spinning robot is a little sticker, a small one about an inch, 2 inches by 2 inches, with a 2D barcode on it. And the robots drive around, they have a camera that looks down, and they look for that sticker. And that's how they make sure that they're staying on track, and they use it as feedback into their control systems. The lines on the ground that you see kind of in this picture are just the leftover rubber from driving precisely in the same places over and over again. So it's left from the wheels. And Raf was the kind of the brains behind the control system. He was absolutely the brains behind the control system and what made the system reliable. And we do a lot of adaptation on board on the robots to make them drive precisely. So this little clip shows the robot driving in a square before it's learned any parameters, and then repeating the square 1,000 to 3,000 seconds later after it's had a chance to learn more of its control parameters. And you can see that second time around, it's like dead on straight. The first time it looked drunk, and now it's shaking it off. And that's all from the feedback that it's getting by driving, using its onboard navigation system, but then getting the feedback from the fiducials that it sees at each corner of the square. And that's all really cool, but I'm going to emphasize a little bit today that it's not really about the robots. The robots are very sophisticated and robust examples of this kind of mobile robotic platform, but it's really the system success is really about the software and the way all these other things integrate and build on the robots to deliver the value. And so the software is probably 8 times harder than the robotic engineering. And if you look at Kiva's engineering teams, we have about 8 times as many software engineers and and networking and IT engineers as we do robotics engineers. So why is that true? Well, as Phil said in the intro, my background, you wouldn't have expected me to end up in a robotics area because I was really working on electronic auctions and e-commerce and these esoteric things called combinatorial auctions, where people can bid on combinations of items. But those were all an approach to solving large resource allocation problems. And so the research group I came from here in Michigan, Mike Wellman's group, was all about resource allocation in large multi-agent systems. So when Mick came to me with this idea and said, do you think we could make this work? I looked at it and said, wow, this is a really cool and interesting, very large resource allocation problem. Which robots should do which activities? And so when I look at the system, I think of it as these 7 major decisions that are being made all the time. The first one is order assignment. So we have a pool of thousands of orders and we have dozens or hundreds of stations. Who should work on which order? And the effectiveness that you make that decision affects how far the robots are going to have to drive to deliver the products. You'd like to assign the orders near where the products already are for that order. Then once you've assigned it to a station, you have to pick the pods that are going to be used to supply the inventory for that order. Then third, you have to pick the robots that are going to deliver those pods to the workers. When you're done with all of that, you store the pods again, and nothing is fixed in the Kiva system. The pods don't have to go back to the same place. When you empty a bin, you don't have to put the same kind of inventory back in it. So everything's dynamic and changing all the time. So where you store it after you're done with it really affects its next use. In addition, there's a pretty subtle and sophisticated algorithm running in the background that has to keep all the robots charged, right? They don't just drive around all day. Every 5 minutes out of every hour, they have to go plug into a charger. And then because they have lead acid batteries, for 6 hours every week, they have to do this thing called equalization if you want the batteries to last for a long time. So there's a scheduling algorithm that's supplying all of that with a limited number of chargers and being aware of the demand that's going to occur to the warehouse over the week. In addition to taking stuff out, of course, you had to put things into the pods in the first place. So there's a kind of symmetric process for putting things into the inventory pods called replenishment. And every time the operator at a replenishment station says, I have some stuff to put away, we have a choice about which bins we bring over to have them stow into. And then behind the scenes, to make all these robots drive around all over the place, there's a lot of path planning going on. And so if you've had any AI courses or advanced computer science courses, you've heard of A*, kind of a standard path planning algorithm. We run that a lot, hundreds, thousands of times a second. And what makes this really hard and interesting is not just the problems, but it's the scale at which we have to solve these problems. So our target size, kind of target for how big a system is the biggest we think we'd ever deliver, has 1,000 stations in it. It would have 10,000 robots all in the same facility, carrying around 100,000 different pods, which are holding 1 million, or that are serving 1 million different lines a day being filled out of the warehouse. And there's something like 10 million different products that are possible to ship out of the warehouse. And we're trying to make these decisions in near real time, right? We have a few seconds. We actually have a few hundred milliseconds to make most decisions that the system has to execute. And we've actually have physical warehouses that have exceeded 1,000 robots and come close on some of these other scales. But we haven't quite hit 10,000 robots yet. But we'll get there. Just to drive it home, so a large Amazon warehouse like the one I showed in that earlier picture, they build buildings that are 1.2 million square feet. So that's about the size of 27 football fields. And imagine eventually filling that with robots driving around. And that's what this facility is going to look like. As a robotics company, we had to make up our own 3 laws. They're very practical 3 laws that help us. The first is don't starve the operator. The reason people buy a Kiva system is to make the people more efficient. So they're spending a little more in capital, but the goal is to keep the people busy. And then where the algorithms mostly come into play is do it with the least amount of equipment possible. So by putting the fast pods near the front, we use significantly fewer robots, and so we're reducing the capital expense for the customer. The third one's unusual, and it's don't do things that look silly. Because it's a real system and people are watching it every day, sometimes the algorithms produce results that a human will look at and say, why is it doing that? That just looks ridiculous. And you go, well, the algorithm told it to plan a path that went like this. And they say, but it should have just come straight in. Why did it have to do that weird little jog? And they're right. And so a lot of times when we're trying to debate what's the right way to do things, if it's going to look silly, that particular solution gets thrown out. And we use this rule actually as much as the other 2 laws. So what are the benefits? Over time, we've proved out a lot of these things. The most important one is the first one on the top left there, and that's the productivity increase. And all of our customers see this 2 to 4x productivity increase. But as was mentioned earlier, that's not good enough if it costs too much. So it's really the return on investment that you have to prove out. And so the operations people will love it, but they have to spend millions of dollars on a Kiva system. They have to convince the finance people that it's a good idea. And those guys don't really care at all about robotics. What they want to see is, does it have this 1 to 3 year return on investment? With the Kiva systems, we have over and over shown that you can increase the output of the building. You can scale the system as you grow. So that's one of the very tangible benefits for our customers. They don't have to buy the whole thing the day they open the warehouse. Instead, they can buy it in pieces and grow it over time. So that video I showed earlier was one of the early Staples warehouses, and that was the very first warehouse we moved into, and it was started with 30 robots and I think 100 inventory pods, and we were just a little corner of the whole building. And as it worked and we proved it out, they grew it, and now that system's over 500 robots and has been running for 7 years now. There's a cycle time improvement because there's no travel time on conveyors or any of that, or people walking around. We can fill orders in minutes instead of hours. There's a few other benefits I won't go through. We'll jump to the last bottom right part there. And one of the key benefits is the very rapid ability, our rapid ability to deploy it, our ability to rapidly deploy it. And we can usually do these systems within 4 to 9 months of someone signing a contract. Whereas most large conveyor-based installations are like a 1 to 2 year design and implementation process. And also one of the unexpected benefits was that you could actually move a distribution center. And this was not something we expected, but it's happened 5 or 6 times now where somebody outgrew the building they had started in and wanted to buy a new building and move into that, and it was somewhere between 4 and 20 miles away. And so an example of that was when Diapers.com in their Reno facility wanted to move from this small facility up here to a much larger building a little out of the city. And so they said, hey, can you guys help us move this thing? It's about 15 miles away. Oh, and by the way, we want to do it in a weekend because we can't afford to have the warehouse down for any length of time. And so we said, hey, most people would say, hey, that's not even possible. Just go build another building. Instead, we say, yeah, that sounds interesting, and can we videotape it? And so we set up some time-lapse photography cameras, and on Thursday afternoon, about 8 o'clock at the end of the shift, people logged out, the operators left, and we started using the robots to drive the pods over to the trucks, wrapping them up in cellophane, putting them on the trucks, driving them over to the new building over here, which we had pre-stickered and installed the server, but other than that, there was no Kiva equipment. We brought everything off the truck. Within 24 hours, we had pods showing up. We had stations being rebuilt in the new location. A few hours later, the robots started appearing. By Friday midnight, all the robots, most of the robots were in place. We start doing testing to make sure everything's working correctly. And less than 48 hours later, we had the system fully installed, moved to a completely different building, and Saturday afternoon, 6 p.m., operators came in. They drove to a different location, different parking lot, much larger building, but they walk into the exact same stations they left. The inventory is exactly the same as it was, and they just started picking full-speed operations. And this was just something that was inconceivable before, and we certainly didn't anticipate it, but we've been asked to do it over and over again. And I think we're going to be asked, we've been asked now to do it, I think it's like a 2-day drive is the next one we're going to do. So that one we don't have to do in a weekend, but over about a month period, we'll be moving pods to a facility that's many, many hours away. So Kiva was pretty successful over the time. We were able to grow from that original 6 people in officially started that part of the growth, got our first funding in January of 2004. Kind of hockey stick growth for the number of employees and also for the revenue. And this is a fun picture we took in, I think, 2012, where Mick had this great idea, let's make a bar chart out of the people about how big the departments are. And so they're organized kind of by department. I can't read them from here, but it's like sell it, design it, build it, deploy it. So all of the departments are organized like that. And then everyone stacked up to show how many people were in that department. And that was when we were about 350 to 400 people. As I mentioned earlier, now in 2012, we were acquired by Amazon, which gives us the opportunity to finally get robots into the world's largest distribution, pick, pack, and ship distribution network. So to summarize, what were some of the lessons, at least that I learned during this process, that were really driven home for me? And the first one is to keep focused, right? The business was not founded as a robotics company looking for an application. We were founded as a business problem for which robotics turned out to be the right application. The second is keep it real. So as we saw in the Webvan business plan, they had unreasonable expectations for how well they were going to do things, and they grew really fast expecting to be able to work those problems out in time, and it didn't work out for them. So we were much more frugal. I think we raised a total of $32 million over the whole life of the company. And Mick had a fantastic business plan from the very beginning. So even very early on, when Raf and I learned about the project and were trying to decide, is it technically feasible and is the business going to work? It felt like it was all feasible. It was just a matter of executing really well. So one of the things that we also really focused on was to always keep the system working. We had a demo system at Kiva, and we had people visiting, investors and customers visiting all the time. It was really important that that always was ready to go for a demo, as our friends told us about earlier today, having your quadcopter fatally crash and having to get it back running in time for some VC guys coming by in the afternoon. We had lots of situations like that. This is Raf pretending to be in a panic because he never really panics, trying to get the system working for a demo that afternoon. We were also really lucky. So I've been involved in a lot of different projects over the years and done a lot of dog and pony shows. And I don't know what it was, but every demo we ever gave worked. We even had a situation once where with this prototype system, which much, much less robust than the ones we built later, we were doing a demo for a potential customer, and we had a different kind of pod. There are these hacked together things in the background. That one doesn't even have its base on it, so it's sitting on the ground. And we were driving, and we were very frugal, so we had fake inventory in the system. It was pretty much the empty bottles and cans and things that Nick had eaten at his apartment, we brought in and put them into the pod. So we had an empty Gatorade bottle bouncing around in the pod as it went over to a station. And without the liquid in it, a Gatorade bottle is kind of top heavy because it has this heavy top. It's still screwed on. So it's wobbling around, and it falls out on the backside away from the customers. It falls out, hits the ground, and bounces up and lands in a lower shelf in the pod, and then drives over to the customer. And they never saw it. We were all on the backside, so we're like, oh my God. And then landed back in, and we could not believe it. So there was definitely some luck involved in the process. And the fourth lesson was know your technical horizon. So we knew we were going to be building really, really big systems, and that these are things going into the heart. When a customer puts this in, it's like doing a heart and lung transplant for their distribution center. Their entire business rides on this thing working. So it had to be really robust and reliable. And so we designed it from the beginning with those concepts in mind. And last was just keep it fun. So if you're going to get involved in a project like this, it's a lot of work and a lot of late nights and a lot of challenging things come up. But as long as you're having fun along the way and you're still interested in the technology and making this and the business problem, it's easy to stay motivated. So we had things like pumpkin carving contests, ping pong tournaments, fun days, softball games, or renting out amusement parks, little amusement parks because we were a little company. And just make sure everyone's having fun while you go through it. And that's all I have. So I can take questions if we want to figure out how to do that in this environment. We can start lunch early. So the question is, do customers rent or lease it? Most of them buy it, but we did have a few. Once we were big enough to support the financial aspect of it, we did start leasing like some extra robots for the peak season to a few of the customers. But for the most part, it's a major capital expense, which they're going to acquire and own and depreciate over time. Yes?
Where does most of your componentry come from? Where is it actually built for your robots? Where do the parts come from?
That's a good question. So where do all the parts for the robots come from? I think we have well over 1,000 suppliers across the whole solution. And I should mention, we don't sell the robots. We sell a solution. And so when you get one of the systems, you get the pods, you get the robots, you get the software, you get all the infrastructure at the station, and you buy licenses to license the hardware and the software to keep so that we will maintain that stuff. So we have a couple thousand suppliers. They're from all over the world. And over time, it's changed. So, we've had local companies supplying parts. What we do now primarily is get components. So we'll have. So it's a big supply chain, and it's not my area of expertise. But we used to get the parts in and then assemble the subcomponents in-house and then put them together into the robot. Now most of the components are, we use sub-assemblers, contractors, to do that part. And they test them, and then they ship them to us. And so we do the final assembly still in-house. And the supply chain spreads from local companies doing very low-volume stuff all the way to China for the pods because the volume there is just so high. Any other questions? Okay. Well, thank you. And we get to eat lunch early.